this section, we're continuing our work with word problems. This time, our focus is percent word problems. Let's start with a review on how to translate and work with basic percent equations. Here, we're simply going to write what we read. Keep in mind that percents must go in as a decimal, so make sure to shift the decimal point 2 places to the left. With this example, we are looking for the percent. Again, we translate, writing what we read. Notice how I use WP to represent the unknown percent. That is my way of reminding me to convert the decimal number to a percentage in the end. In the end, you see the decimal point shift 2 places to the right with the percent symbol attached to that number. Here is our first mixture problem. Although this problem is contrived, it can still be modeled if necessary. We're mixing pure water with a 70% antifreeze solution to gain antifreeze that is 60%. We're using the water to dilute the 70%, again for the 60%. The question is, how much water is necessary to do this if we have 30 gallons of the 70%? With mixture problems, I always organize myself with boxes. The top 2 boxes represent the 2 solutions being mixed. The bottom box represents the final concentration, final solution. In each box, we will need to put in the concentration and how much of that solution we are using. We must be consistent with the meaning behind the concentration. So as you can see, all of the solution's concentrations are stated with percentage antifreeze. The water is pure, therefore it's 0% antifreeze. The author wants us to find how much water should be mixed with 30 gallons of the 70% solution. These numbers are placed in their boxes. If we mix X gallons and 30 gallons, how many gallons do we have in the end? At this point, we can only state this as an expression, X plus 30. Now we bring in the formula we need to set up the equation to solve for the unknown. This formula says when we multiply the concentration by the volume, we get the amount of antifreeze. We will set up our equation by adding this product of the 2 concentrations we are mixing and setting this equal to the product for our final solution. Every term in an equation must mean the same. We have that with the concentration multiplied by the volume for each term. Before we can solve the equation, we need to convert the percent numbers to decimals. With the second step, we're multiplying and distributing for X equals 5. Look where X is in our boxes. This says we need 5 gallons of pure water to get that final concentration the author needs. One more thing to reflect on. This can help us check the reasonableness of our answer. Notice how the final concentration of 60% is much closer to the 70% than 0%. So if we're mixing 2 solutions and we want the final concentration to stay fairly high, this means we are not going to need much water and would therefore need much more of the 60% solution. In the end, we figured out we needed only 5 gallons of water in comparison to the 30 gallons of the 60% solution. Use this type of reasoning to check the reasonableness of your final answer. Here is another mixture problem. We will set up the boxes again to organize the information from the problem. This problem is different in that the total volume is given. So we're going to have to recall how we split up a total into 2 parts. We talked about this earlier in this chapter. If one of the solutions has an unknown X liters, then the other part will need to be the total minus the first part. Once the boxes are filled with the concentration and the volume, we are ready now to create that equation that will allow us to solve for our unknown. We will need to find concentration times volume for each box. Add this product for the 2 solutions being mixed and set this equal to the product for the final solution. change the percents to decimal numbers, and then solve the resulting equation. If we need 12 liters of the 25% acid solution, we will need 30 minus 12, or 18 liters for the 50%. With 50% closer in concentration to the 40, we will need to see that we require more of the 40%, and we do have that. Here is one more mixture problem. We're not mixing solutions, but rather coffees. Just like with the previous mixture problems, create the boxes and make sure to get two numbers in those boxes. The product of these two numbers has meaning as well. This time it represents the value of coffee for each case, each box. Write the sum of these products, of these coffees being mixed, and set it equal to the product for the final. Solving, we get x equals 7. The cost of the final coffee is $5 per pound, and it is closer to the second box than the first. It is $1 per pound away from the $4 coffee, and $2 away from the $7 per pound coffee. This means we will need twice as much of the second coffee than the first. And isn't that how things worked out for us? If we had reasoned this out at the very beginning, we wouldn't have needed to work through all of this work. Hopefully this has been helpful. Before you submit your final answer, always check the reasonableness of that answer by comparing what you are mixing. Thank you.